right?
I guess. All right, our next section, we're going to look at section 5.3, and it's going to be all about a specific type of probability distribution that's called the binomial distribution. So a binomial experiment is going to be a probability experiment that satisfies the following 4 requirements. Okay, so let's look at each of these. So it says that there must be a fixed number of trials. So that just means that you can't do your experiment an infinite amount of times. At some point, it's got to end. Each trial can only have 2 outcomes. So that's probably the most important feature of a binomial experiment. So the bi in binomial means that there's only 2 outcomes that can happen. Okay, and then we label these as either being a success or a failure. Now, those words, they don't have anything to do with like our typical English definition of success or failure. It's just simply the labels that we give to those 2 outcomes. So it has nothing to do with like being good or bad. The third requirement is that the outcomes of each trial must be independent of one another. And then the fourth is that the probability of a success must remain the same for each trial. Okay, and then off to the side there, it says that the outcomes of a binomial experiment and the corresponding probabilities, when you put those together, we get what's called a binomial distribution. So before we get into like the actual problems, let's just first practice seeing if we can recognize whether or not an experiment is a binomial experiment. Okay, so we just want to check those 4 requirements for each of these parts here in example 1. So let's see, A says that we're selecting 20 university students and recording their class rank. Okay, so there's a fixed number of trials because I'm selecting 20 students. I'm not selecting an infinite amount of them. Let's see, if we record their class rank, how many possible outcomes could we have there? Do you want to answer that? Yeah.
4, 5, I don't know. Sometimes people take victory laps.
But I guess the point being is that there's definitely more than 2, right? Yeah, so since there's more than 2 outcomes, that tells us right there that no, this is not a binomial experiment because there's more than 2 outcomes. Okay, so at that point, we're done there. So B says selecting 20 students from a university and recording their gender. Okay, so again, we're selecting 20 students, so we have a fixed number there. How many outcomes are there for gender?
I mean, in 1950, I'd say 2. Today, probably it's a little more fluid than that.
Yeah, so this textbook was written at least kind of a while ago. So when this was written, there was definitely only 2 genders, we would say. So so far that's good. So there's 2 outcomes there. The outcomes are independent of one another. So when you record one person's gender, it's not going to affect the gender of what the next person tells you theirs is. So they are independent. So yes, that would be a binomial experiment. Okay, part C says selecting 5 students from a large school and asking them if they are on the dean's list. So we're selecting 5 students. What are the outcomes there when you ask someone if they're on the dean's list?
Yes or no?
Yeah, yes or no. So there's only 2 outcomes there, so that's good. Are the outcomes independent of one another?
Yeah.
Yeah, I mean, the answer that one person gives you isn't going to change the answer that the next person gives you. So they are independent of each other. And those are the 2 main things that you're really checking here. So yes, that is a binomial experiment. And then part D says drawing 5 cards from a deck without replacement and recording whether they are red or black cards.
I'd say, I mean, I want to say yes because it's just red or black, but then there's also like you're not replacing it. So there's some dependency on what you picked previously.
Yeah, exactly. So there's 5 cards. So there's a fixed number of trials. Red or black means there's only 2 outcomes. But the fact that it's without replacement means that the trials are not independent of each other. So since you're going to hold on to a card, that's going to change the probability of the next card that you draw. So that would not be an example of a binomial experiment. So for this section, we're just going to stick with working with binomial experiments and answering questions about their probabilities. Okay, so you can see in your notes there the formula that we have to figure out probabilities that are associated with binomial experiments. So it's a pretty complicated formula, I guess, kind of. Let's make sure that we know what everything stands for there. So the number of trials is going to be that lowercase n. The number of successes in n trials is your capital X. The probability of getting a success is going to be P. And then the probability of a failure, well, since you only have, well, the notation for that is a lowercase q. And then since you only have 2 outcomes, if you know the probability of a success, then to get the probability of a failure, it's just going to be 1 minus that, because we know that the sum of probabilities has to add up to 1.
Mm-hmm.
Okay, so let's do an example and we'll practice with the formula there. So example 2 says that a coin is tossed 6 times. Find the probability of getting exactly 2 heads. Okay, so n is going to be the number of trials. So we're tossing our coin 6 times. X is going to be whatever we're trying to like figure out. So the probability of getting exactly 2 heads. So X is going to be equal to 2. P is going to be the probability that you can get heads when you toss the coin. So we obviously know that that's 0.5. And then Q will just be 1 minus P, so 1 minus 0.5, so that's also 0.5. Okay, so we're going to plug in all of those values into that formula there. And for our notation, like in parentheses next to your capital P, you're just going to put what X equals. So we'll say the probability of X being equal to 2, and then we'll fill in our formula. Okay, so we have 6 factorial over 6 minus 2 factorial times 2 factorial. And then we're going to times that by P raised to the X power. So times that by 0.5 to the 2nd power. And then times that by Q to the N minus X power. So that'll be 0.5 to the 6 minus 2. Okay, and then you kind of struggle a little bit to type that into your calculator correctly. You're welcome to try that if you want right now. If you're going to do it, just definitely put parentheses around your entire denominator. So you can see if your answer matches what we got. So you should get 0.234 when you round to 3 decimal places. Now, if you did just try that in your calculator and you found that to be a little bit tricky and you didn't get the right answer, that's okay. So luckily for us, someone at one point did program this formula into our calculator. So we can actually bypass having to do the formula ourselves, and we can just use the calculator to help us figure out these values. So there are 2 different binomial functions that are stored in your calculator. So I'll show you what both of those are. The first one you can use whenever you're figuring out the probability that X is exactly equal to some number. Okay, when you have that, you're going to go to a place in your calculator where it says binomial PDF. So binomial probability distribution function. And then it's going to want 3 different inputs. So your calculator is going to want to know what N is, what P is, and what X is. Now, the other thing that your calculator can do is it can add up multiple probabilities for different X values. So it can also figure out the probability that X is less than or equal to a certain number. So in that case, we're going to go to a function called binomial CDF, where the C stands for cumulative, because it's going to add up a bunch of X values for us. And it's going to want to know the same 3 inputs, so N, P, and X. Okay, so the important thing to notice here is that when you're figuring out the exact case where X is equal to some number, that's going to be binomial PDF. And then when X is less than or equal to some number, that's going to be binomial CDF. So 2 different places. To find those are listed under your distributions, which you get by doing second bars. So that'll give you your list of distributions, and you'll find both of those in those lists there. Okay, so let's do example 3, and we'll just use our calculator now instead of the formula. So it says a survey found that 1 out of 5 Americans says he or she has visited a doctor in any given month. If 10 people are selected at random, find the probability that exactly 3 will have visited a doctor last month. Okay, Dr. Insko, I'm going to ask you some questions here. So can you tell us what you think N is?
I think 10, because 10 people are selected at random.
Good. So N is the total number of people, so 10. What is X going to be?
X is going to be the number of people going to the doctor, so 3.
Yep, X is exactly 3, so X equals 3. And then what would the probability of someone saying that they have visited a doctor in the last month be?
1 out of 5, so 1/5 or 0.2.
Perfect. So it says 1 out of 5 Americans says they've visited a doctor in any given month, so that's just 1 out of 5 or 0.2. Okay, so we want the probability that X is equal to 3. So since this isn't an exact case, do we want binomial PDF or binomial CDF?
PDF, because we want, yeah, exactly that.
Good, so we want binomial PDF, and then we just need to tell the calculator N, P, and X. So, and they have to be in that order. So it'll be 10, comma, 0.2, comma, 3. So in your calculator, whether you're using the 83 or the 84, it doesn't matter. You're going to do second bars. Let's see, binomial PDF is, you have to scroll down on your screen. It's actually choice A. So you'll select that. Now, if you have the 83s, it's just going to put binomial PDF like up on your screen, and then you're going to have to type in 10, comma, 0.2, comma, 3. Okay, and then you'll click enter. On the 84s, it's just going to ask you for these things. So it's going to say trials, you'll put 10 in, P, you'll put 0.2 in, and then your X value, you'll put 3 in.
And for this class, I think we're using a simulator, right? So that's typically an 84.
Yeah.
Okay.
So on the simulator calculator on your computer, that's usually the easier input. So it's just going to like ask you for those. So you don't have to worry about like typing them in necessarily. Okay. So either way though, you should be getting approximately 0.201 when you round to 3 decimal places. So about like 20.1%. Do you have any questions on that one?
No, that's good.
Okay, so let's do another example. So example 4 says that a study reported that 10% of Americans are afraid of being alone in a house at night. If a random sample of 20 Americans is selected, find the following probabilities. Okay, so we have a bunch of different parts here that go with this question, but what I usually like to do is just kind of note down for myself what N and P are, because those aren't going to change as we go through the different parts. The only thing that's going to change is what our X value is. Mm-hmm. Okay, so N is, let's see, it's the total number of people, so this would be 20. And then P is going to be the probability that they give us in the question. So it's 10%. So P is going to be 0.1. And it's good to note what that probability actually corresponds to. So it's the percent of Americans who are afraid of being alone in a house at night. So we just want to keep that in mind, that that is what that probability goes with as we go throughout each one of these questions. Okay, so part A says we want the probability that there are exactly 5 people in the sample who are afraid of being alone at night. Okay, so exactly 5. So whenever you see the exact case, that's kind of the easy one. So we just want the probability that X is equal to 5. So for exact, we're going to use binomial PDF, just like we did in the last example. And then we'll fill in that N is 20. P is 0.1, X is 5. Just put all of that into your calculator and you'll get a probability of approximately 0.032. Okay, so the exact case, like I said, is kind of the easier one. So let's see if they get a little bit more interesting. So in part B, we want the probability that there are fewer than 4 people in the sample who are afraid of being alone at night. Okay, so fewer than 4. So if I translate that algebraically, do you agree with me, Dr. Insko, that that would be the probability that x is less than 4?
Yeah, so 0, 1, 2, or 3.
Yeah, good. Okay, now that's correct, but the problem is that our calculator, there's no like function built in there for the strictly less than case. Okay, your calculator only knows 2 things. It knows the exact equals to case or less than or equal to. So what we want to do is try to translate this into the less than or equal to case. So what I'm going to do is write out like all of my possible outcomes here. And you may or may not like find this necessary to do. Like you might be able to just think about it in your head and come up with how to rewrite this. But if you're more of a visual person, you know, this might help you. So our possible outcomes are, you know, 0, 1, 2, 3, 4, 5, all the way up to 20. So we want the outcomes where x is going to be less than 4. So we want the outcome of 0, 1, 2, or 3. So what's another way that I could write that with a inequality symbol of less than or equal to?
Less than or equal to 3.
Yeah, less than or equal to 3. So the probability that x is less than 4 is the same thing as the probability that x is less than or equal to 3. Okay, and the whole reason we're having to do that is so that we can use our calculator for the less than or equal to case. Okay, so for less than or equal to, that's going to be binomial CDF. So binomial CDF, and then it's the same inputs of NPX. So N is 20, P is 0.1, and then X is 3. So you'll put those into your calculator and you'll get approximately 0.867. Any questions on that one?
So that's saying that there's an 86% chance that 3 or fewer people are afraid of being alone at night. Is that right? Or?
Correct. Yeah. If you have that random sample of the 20, or if you're picking a random sample of 20 Americans.
Gotcha. So most people are not afraid of being alone at night.
Yeah, because only 10% are.
Okay. Yeah. Okay.
Okay, so part C, we want the probability that there are at least 4 people in the sample who are afraid of being alone at night. Okay, so how do you translate at least 4 algebraically? Like, how do you make that an inequality?
4 or more, I think.
Yeah, so what inequality sign would that be?
Greater than or equal to 4.
Yeah, so that's the same thing as saying like the probability that x is greater than or equal to 4. Okay, so can we put greater than or equal to 4 in our calculator?
No.
No, remember we only have 2 options. Yeah, equals or less than or equal to. So we have to now figure out, all right, how do I still get that same probability for greater than or equal to 4, but put it in terms of less than or equal to so that we can use our calculator. So again, I'm going to kind of sit here and list out all of the possible outcomes for selecting 20 individuals. Okay, so we want the outcomes where x is at least 4. Okay, so that would be the outcomes of 4 people, 5 people, 6 people, 7 people, all the way up to 19 people or 20 people. So those are the probabilities that I want. Okay, so what we can do here is we can use the fact that the sum of all of those probabilities, if you add them up, what do they have to equal?
1.
1, yes. So the sum of all of those equals 1. And what we can do is say, all right, I'm going to start with knowing they all equal 1 when you add them up. And then I'm gonna basically subtract off the ones that I don't want. And I don't want the 0, 1, 2, or 3. So how do I represent the ones that I don't want? Well, I could say that that is the outcomes where x is less than or equal to 3. So the probability that x is greater than or equal to 4 is going to be the same thing as 1, which is the total, minus the probability that x is less than or equal to 3. So you can just think about it as like you want 4 and above, so you don't want 3 and below. So you take 1, which is the total for all of those probabilities, and then subtract the ones that you don't want. Okay, so then in your calculator, you can just do 1 minus, then go to binomial CDF, and then do 20, 0.1, 3, and you'll get approximately 0.133. Any questions on that one?
No.
Okay. So then part D says that we want the probability that there are between 6 and 10 inclusive. That means we are including those values. People in the sample who are afraid of being alone at night. Okay, so between 6 and 10, I can write that as a compound inequality, just like that, where we have that 6 is less than or equal to x, which is less than or equal to 10. So again, if I kind of sit here and write out all of my outcomes in the sample space, that's from 0 to 20. And I'm just going to circle the ones that I'm actually trying to find. So I want the outcomes where x is equal to 6, 7, 8, 9, or 10. Okay, now since we're stopping at 10, I don't want to do this one the exact same way that I did the previous one where I said that the total sum is equal to 1. Okay, that's not going to be really helpful because it doesn't go up to 20. So what we can do is something similar where I say, all right, well, what if I figure out the total probabilities for the outcomes of 0 up to 10, because I can represent that as x being less than or equal to 10. And then which ones don't I want?
You don't want the ones that are less than or equal to 5.
Good. So I don't want 0 through 5, and I can represent that with a less than or equal to sign where we write it as x is less than or equal to 5. So the probability that x is between 6 and 10, I can write that as the probability that x is less than or equal to 10 minus the probability that x is less than or equal to 5. So the less than or equal to 10, that's capturing all of your probabilities for the outcomes from 0 to 10. And then we're subtracting off the ones that we don't want. So we don't want the ones that are lower than 6. So we take off the probabilities for x being less than or equal to 5. Mm-hmm. So that's just going to be 2 different binomial CDFs. So you can still do it in like one line in your calculator. So it'll be binomial CDF. You'll fill in 20, 0.1, and 10. And then keep that like in your calculator and just do minus, and then go get another binomial CDF and do it with 20, 0.1, and 5. And then you should get about 0.011. So can you like see any sort of pattern there maybe for the between 2 numbers case?
So you want to include the larger bound, but exclude the lower bound? Is that what you're saying? Or go 1 less than the lower bound?
Yeah, so that's usually what I point out. Like if it's between 2 numbers, like it's going to be the probability that x is less than or equal to the larger number exactly. But then when you subtract the other probability, it's always going to be like 1 minus whatever that lower bound is, like you said. Okay. Yeah. So it's kind of like a common thing for students to just put like 10 and then 6, but that would be wrong because then you're removing the 6 as well and you want to keep the 6. So just remember that that second number is the one that you have to drop down by 1. Okay, and then there's just one more here. So part E, we want the probability that there are at least 14 people in the sample who are not afraid of being alone at night. Okay, so now we get to see if we've been paying attention to like the words in the question. So Dr. Insko, do you recognize what's different about part E?
So yeah, it looks like we've been saying who are afraid, now we're saying who are not afraid.
Yeah, exactly. So
The
for
wording
this,
is just slightly different.
yeah, the wording is different. So now this is kind of like asking a question associated with the failure, whereas the probability that we recorded in the beginning was the probability of the success, which was just deemed, you know, people who are afraid of being alone at night. So you do definitely have to read the question carefully. And what I would do is that if it gives you like the other one, you always want to try to like put it in terms of the original question. So at least 14 people who are not afraid. Ultimately, that's what we're looking for. But let's see if we can translate that into people who are afraid. So if there's 20 total people and at least 14 of them are not afraid, what does that mean as far as how many are afraid?
Is that 6 or fewer are afraid?
Yeah, so that would be, we could write that as like the probability that at most 6 are afraid.
Okay.
That makes sense so far?
Yeah, so that's less than or equal to 6 are afraid.
Yeah, good. Okay, so we turned it from are not afraid into are afraid, and now we'll just translate that into an inequality. So at most 6 just means, you know, the outcomes of 0 through 6. So that's good because we can write that with a less than or equal to sign, which is good because we can just put that right into our calculator. So we don't have to do anything extra with this one. We'll just do binomial CDF with 20.1 and 6. And we get a probability of approximately 0.998. Any questions on that one?
No, it just seems like the hard part there is doing that translation, I guess.
Yeah, so just remember that like if you have to switch between like the opposite probability as far as like success and failure, at least will turn into at most will turn into at least, and then you're just subtracting the amount from the total amount of people. So at least 14 turns into at most 6. If it had been at most 14, that would turn into at least 6, and vice versa. And again, like this is kind of this is the hardest one of all of them. And they do just take practice. So there's a good amount of these on your homework in Connect Math. So, you know, even if you're getting them right, you can still do like try a similar problem and redo a bunch of them until you get the hang of it.
Cool. Yeah, it's definitely something where once you get practice at it, you become fluent with what they're trying to say.
Yep. Okay, so that's the end of section 5.3 and the end of chapter 5.
Cool. Thank you, Karen.